Okay, so it's working on YouTube as well now. Okay, now for the chats. Let me see the chat. Uh, so here's the chat for Steam or for Twitch, and I'm not too sure about YouTube, how to configure it for YouTube at the moment. So I'll just put it like this for now. And let me mute myself on Twitch. Okay, testing on YouTube. Yeah, I think the audio is too low. Let me increase the audio a little bit. Okay, perfect. So, I don't know what's the name of the stream. Yeah, it should be Learning AI and Software Engineering. I think it's the same. Oh, it's not the same on Twitch. Wait, let me change it. Uh, uh, let's say learning, reading machine learning, or reading AI research papers and software development. Okay, so I think I changed the name on Twitch. There we go. Perfect. Mm-hmm. Uh, yeah. So, the first thing is my research paper. And yeah, so basically I'm going to try to implement Alexnet and yeah, I need to see a better way how I can. I need to get a plugin for multiple chats, to be honest. Um, how do I do this stupid chat thing? Um, there we go. Okay. I have to figure out the chat thing afterwards. I have to download like a proper plugin for this. But anyways, um, yeah. Okay. Hello and hello. All right. So we were implementing ImageNet. So current approaches to object recognition makes essential use of machine learning. Yeah. So I was reading this entire research paper um in another stream, and I also was reading it a little bit off the stream as well. And there's a lot of very important information, which is pretty nice to know. And I'll highlight those and also, I mean, understand them. So, for example, this one, which is the local response normalization, what's the difference between normalization, standardization, and so there's normalization, regularization, and standardization, right? So what's the difference in between all of those three things? What's the difference between layer norm, batch normalization, and what's this thing with the local response normalization? What's overlap pooling, and then what's the overall architecture? But most importantly, what's very important is that we look at Pytorch GitHub page. Hopefully they have already an implementation um, or examples that we can use. So let's take a look if they have anything over there. Um, fast and lean installation, Docker image. Let's see this. Yeah, anyways, some Docker documentation getting started. Then there is nothing much useful. GPU, tensor, fast and lean. Nope. I have to find where it is it. Where are the examples? Okay, benchmarks. Um, PyTorch examples. Examples. There we go. So they have, I think so they have tutorials, they have recipes, which is over here, available models, Alexnet, nothing over here. Um, Let me just search it directly on on Google. PyTorch Alexnet. So this is their documentation. So this is that it's a 2012 paper. You can open it in Google Colab. So this is where they've basically identified whatever information that you need. Um, and yeah, and that's probably um uh this is where they're defining the entire architecture. Um, so if you look over here in the PyTorch Vision, Torch Vision models, alexnet.py, this is where they're basically defining um, how they've implemented the entire AlexNet, where they have your number of classes as 1000, your dropout as 0.5, and so on and so forth. So we'll be looking into this. I'm just taking a look at other implementations or documentations before I start. to implement this. But yeah, I think that's pretty good starting point for now. Um, yeah, let me just couple all of this into a single tab, so it's more easier for me in that way. Papa, papa. And you go all the way there. Okay, so to implement or to first read, this is very important. Um, yes, very, 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 very important. Uh, okay. So, a quick recap. Um, let's just go over everything. So these were the results that they said that this was the data set or the competition where they got like 26.2% error rate. They were decreasing it from like 47 or something to this much. Then until recently data sets of labeled images were relatively small, on the order of tens of thousands of images. Then they also discussed other data sets. So for example, Label Me and ImageNet. And then I said that, hey, I need to look into this more detail, which is their capacity can be controlled by varying the depth and the breadth, and they also make strong and mostly correct assumptions about the natures of images, etc., etc. So I have to like look into what do they mean by stationary of statistics and locality of pixel dependencies. Then there was this thing which is our network contains a number of new and unusual features which improve its performance and reduce its training time, which are detailed in section 3. So they're basically like explaining how um, they were improving the performance and reducing their trading time by basically reducing overfitting by applying ReLU. They were doing data augmentations. They were then also applying normalization even after they had applied ReLU at a layer level um, or not a layer level, but they applied normalization again at a local response normalization way. Um, then they also explained that there were human laborers which were used, and then we get an information about the ImageNet, which is that we have 1,000 images in each of the 1,000 categories, so there's like 1,000 by 1,000, so that's 1,000,000 images almost, um, or not one, yeah. And they said that they had roughly about 1.2 million training images, out of which no, they had 1.2 million training images, and that they had 50,000 validation images, and they had 150,000 testing images. So they were basically using like a subset of that. Then we have the um, we have then the evaluation metrics, the pre-processing of the data set. Then we have the sigmoid activation function. We have why do ReLUs run or train faster. So you're basically comparing a sigmoid function over here with your tan function, and you're saying that sigmoid functions are like saturating because when you're increasing the value, then that basically means that they will like become constant. So if you have like um like a sigmoid graph, so it looks something like this, and then it becomes parallel or tangent when the values become too big. So that's what they meant by saturating nonlinearities. Also with tan h and also with the sigmoid function, but with ReLU, it not only trains faster, but it also mitigates that problem as well. And then they were explaining all of that over there. Then over here, they were basically explaining how they were achieving the parallelization, or the GPU parallelization trick over here. And then we have more additional information related to this. Um, yeah. Then comes the other part, which I didn't discuss, and I'm now going to understand and try to implement that. Not implement, but try to understand for now. So we have the local response normalization. ReLUs have the desirable property that they do not require input normalization to prevent them from saturating if at least some training examples produce a positive input to a ReLU. Learning will happen in that neuron. Yes, because um, when you have a ReLU function, it's like this. So um, you do not require any normalization for it to basically reduce the saturation, because whenever you have a positive input, learning will still take place, because the values are increasing and the gradient, there's also a gradient. Another reason why sigmoid function and tanh functions doesn't work is because the gradient over here is 0, so there is no learning being involved, which sucks. However, we still find that the following local normalization scheme aids generalization. So they're still saying that, hey, even though ReLU is not having any saturation, but for generalization, for reducing overfitting, it's still better that we apply local response normalization, denoting by AIXY the activity of a neuron computed by applying kernel I at the position XY and then applying a ReLU nonlinearity. The response normalized activity BIXY is given by this expression. So now let's try to basically break this equation down and understand what do they mean by this entire thing. So let me quickly just remove these things and use a chat tool or an LLM to help me out. So let's take a look again. Okay, so the original activation of a neuron computed by applying kernel I at position XY. What do they mean by this? Okay, imagine a single layer in the network as a start of many different versions of the same image. Sorry. Each version has been filtered to look for a specific feature like edges, colors, or textures. Okay. Spatial location, X and Y. Think of this as a specific pixel coordinate on the map. If the layer is 55 by 55, then XY tells you where you are standing on that grid. Example, row 10 and column 20. So X and Y is the pixel location, okay? Kernel index I. This represents the depth of the flavor of the feature. Each kernel also, so I equals to 0. So I is basically saying which kernel you're basically applying over there. Okay. So um uh so you have your kernel, right? And then you're sliding your kernel. Okay. Mm-hmm. Uh, um okay, so let me see if I can change the screen. Or maybe it's better that I don't do that and instead use this. Okay, and let me switch the screen to to what? There we go. Perfect. Um, yeah. Okay. Getting back to where was I? Here, here, and here. Okay. So, um, let's try to visualize this a little bit. So let's assume that we have a random image, a random 5v5 image. Where should I put the mic? Maybe like this. Nope. Maybe here, like that. Okay. I hope that I'm still audible, but why is it behaving like this? What just happened? Okay, so this is correct. This is correct. This is correct. Oh no, it's because it's inverted. It's inverted. No one. Uh, and that's not good. That's not good. That's not good. There's an option for 270 degrees, but there's not an option for 360 degrees. Why is there not an option to do 360 degrees? I wanna like flip. Uh, Tell me why think nothing but a bomb. I did not thought about this. This is a problem. Problem. This is not good. Not good at all. This is not good, not good, not good, not good, not good. Hmm. Let me think what to do, 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 what to do. Why, 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 Huyon, why? This will also not work, right? Thing is now even the normal thing is not also working. Thing I messed up with the calibration, the monitor calibration. Oh, it works, it works, it works. All I had to do was just flip it. Okay, it works now. It works. Perfect. Perfect, perfect, perfect. It works. Okay. Um, all right, so coming back to what I actually wanted to do. Huh. Um, so we have a 5 by 5 image. So we can say that this we have some values like 10 and the thickness is too much. So we have like 10, 10, 200, 200, 200. And then we have another one 10, 10, 200, 200, 200, 10, 10, 200, 200, 200. And then we have 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. So we have a 5 by 5 image. And then we have a 3 by 3 kernel. So a 3 by 3 kernel looks like this: -1, -1, 0, 0, 0. And then we have 1, 1, 1. So this is our kernel, which is basically our 3 by 3 image. And this is our 5 by 5 CNN image. Perfect. Um, then we're basically grabbing this entire thing, and now I know why this should have been better on Paint, because then I can like just grab it and then put it over there. Can I do that? Let me see. This. Maybe I can do it, but I'll have to check. So I have to group them. Yes, I can. Kind of. So I apply this kernel over here, then here, and then here, and then here, 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 and then here. So that's how the kernel is being applied. So when we do the first operation, right? So we have, or we could say that we have a 110. So this was basically represented as what now? So this was a x comma y I. So when I say x and y, so let me just label this as well. So this is 0, 1, 2, 3, 4, and this is 0, 1, 2, 3, 4. So when I say 1, 1, I'm talking about this one. And when I'm saying I 0, then that should mean that I am placing the center of the kernel over that image. So that basically means that we take our group and we place it right over here. So that is the first one, right? And then you get -10, you get 0 over here. So you're basically applying a dot product. So what dot product basically means is you just multiply them and then you add all of the values. So that would be -10, 0, 200, -10, 0, 200, -10, 0, and 200. So that would basically give you a total value of 570, and that is basically um, telling you that that you have found a very strong vertical edge. So this is how we're reverse engineering what XY basically means. So XY is basically your pixel, and your I is where you're basically keeping your kernel, right? So so you can imagine that you have like different kinds of kernels over here. So not just this one, but there's another one, and then there's another one, and so on and so forth. And maybe in this one, you could have like -1, -1, -1, and then 0, 0, 0, and then 1, 1, 1, 1, 1, something like that. And then you have like all sorts of those things. And that you're saying that um, this is basically your I, which is like telling you which kernel are you applying. So X and Y is basically telling you um, uh, X and Y is basically telling you um, what um, at what position of the image are you basically applying your kernel to, and your I is basically telling you which kernel you are applying. So that simplifies a lot, because now if we take a look over here at our equation, um, X and Y, we know what X and Y is, and we also know what I is, and we know what this whole thing is doing, and it's just applying the convolution. Um, so we have figured out what is the first part of the equation. Then comes the part about the summation. Okay, this is the most unique part of the Alexnet math, which is the adjacent kernels n. So what is this n thing? Where the sum runs over n adjacent kernel maps at the same spatial position, and the bigger n is the total number of kernels in the layer. So the bigger n is here, and then the smaller n is the adjacent kernel maps. So local response normalization looks at the neighboring kernels, the layers above and below it in the stack. The formula looks at the kernel I and sums up the squared activities of its neighbors from I minus n divided by 2 to I plus n divided by 2. So the logic, if you have like 96 kernels, n equals to 96, and you're looking at kernel 10 with n equals to 5, So n is basically like telling you how many adjacent kernels you could look at or how many neighbors you could look at, I assumed. Then if you're at 10, then you look at 9, 8, um, or 5 isn't in total. Okay, so 5 isn't in total. So that means you would look at 8, 9, 10, 11. So 8, 9, 10, 11, and then 12. So 10 is your center. So two before 10 and then two kernels after 10. So that the 11th kernel and the 12th kernel. And the effect is called the lateral inhibition. So lateral inhibition basically comes from biology. This is again what Gemini was basically telling me. And lateral inhibition, when I saw a video of uh, outside the stream, it was basically an idea where it was explaining how we can differentiate different objects in dim lights, or how can we differentiate objects based on contrast. And what our brain basically does is that, not our brain, but basically what it does is that when one neuron is activated or it is energized, it looks at its surrounding neighboring neurons and it decreases their activation. So what it does is, imagine if you have one neuron over here, and then you have, let's say this is neuron 1, this is neuron 0, and this is neuron 2, and this one is basically your activated neuron, and this is connected. So if this one is activated, it decreases the activation of this neuron and this neuron. And what that does is it allows you to have stronger contrast. So when you look at it up at an image, for example, like if there is like a ground and then there's like a tree or something like that, um, what our neurons are basically doing is, if this is an RGB neuron, then with the surrounding neurons, these neurons are activated, these neurons are deactivated, so it allows you to have like a stronger contrast between these sharper edges. So that's basically what is lateral inhibition in biology, and that's the principle or the logic that they're using over here. So similarly, in our case, if we have a kernel over here as kernel 10, and then we have a kernel 11, um, sorry, 11 will come after that. So if you have a kernel 11, 12, and then you have kernel 9 and 8, and this one is your main kernel, then this is called lateral inhibition. If many different kernels are all screaming, I found something at the same exact same pixel, the normalization dampens them all so that only the strongest and the most unique signals survive. So instead of all of them, you're just using like these neighboring ones, I think. Okay, so neighbors, n is how many nearby feature types are checked for competition. So I equals to 0 might be a map of all of the horizontal edges, I equals to 1 could be the map of all of the blue colors, and I equals to 2 could be the map of all of the circles. Okay, now let's try to understand the locality. The local and the local response normalization refers to the locality in the stack of pages, not locality on the image surface. The comparison, when the model looks at the value at x comma y on page 10, it looks at the values at the same at this exact same xy spot on page 8, 9, 11, and 12 if n equals to 5. If the page 10 says I found an edge, but the pages 8, 9, 11, and 12 also are screaming very loudly, it means that the spot xy is generally noisy or overactive. The formula divides the original value AXY by the sum of these neighbors. This pulls down the value if there's too much competition, ensuring only the most distinct feature stands out. Okay, numerical example. Suppose we are at a pixel 10, 10 and we look at kernel I equals to 3 with n equals to 3. We look at the raw activations of the spots for kernels 2, 3, and 4. Okay. If a square, if for a2 the value is 2, a3 the value is 10, and a4 the value is 2, the competition is low. So let me just write this down. If a2 the value is 2, so you have kernels as 2, 3, 4, and the neighbors were 3, so that's basically your 3. A3 is basically 10, A4 is 2. The competition is low, so B cube is high. If A2 is 50, A3 is 10, and A4 is 50, the neighbors are massive. The formula will divide A3 by a very large number, making the final B3 very small. Okay, maybe a little bit understanding. Okay, because only the third one is strong over here. It found a feature that its neighbors kernels 2 and 4 could not. The math interpretation, the denominator in the LNR formula remains small because that's the sum of the squares. So where's the formula again? This is the formula. So the formula is basically, so you have 10 divided by sum k plus alpha, and then from n minus 1, so from all of the kernels, so okay, let me enter some values. So a, maybe a2 10 comma 10 divided by k plus alpha, and let's assume that there were 3 kernels in total, so the minimum of 3 minus 1, so 2 comma I plus 1, so that's 2 plus 3 divided by 2, and then summing it, maximum of 0, I minus, so 2 minus 3 divided by 2, and then a2 10 10 squared to the beta. Okay, a10, so the denominator in the LRN formula remains small because the sum of the squares, which would be, so you start with this would be j, right? Sorry, this would be j. So that means you start from 2, and then when you do this, so 2 plus 1.5 will take the roof. The roof. So 2 plus 1.5 would be 3.5, so till 3, because there are only 3. And then 0 to 2 minus this, so 2 minus 1.5 would be 1.5. So let's take maybe like 1 or 2 in this case. And this will be 4. So the minimum of 2 or 4, 2, and the maximum would be 2. So that means you will start this entire loop from 0. Oh, wait, the maximum. So this will be, I think, 1, and this one will be, I think, 3. So you start from 1, I think. Um, no. I was right. I was right. I was right. Sorry. So this will be 4, and then 2 minus, because the current, sorry, the kernel was 3, right? So 2, uh let's take this as 3. That's this. Then 3 plus 3 divided by 2, 1.5, 4. And then over here, that's 0. And then 3 minus 1.5, that's again 1.5. So let's take 2. So we start from 2 and end at 2. That doesn't make any sense. Where am I going wrong? Why is the math not mathing? Okay, to understand the summation limits like I plus n divided by 2 and I minus n divided by 2, think of it as a sliding window that moves through the thickness of your kernel stack. I is the index of the kernel you are currently normalizing. N is the width of the normalization window. So Alexnet uses n equals to 5, and total n is the total number of kernels in that layer, example 96 in the first layer. So the lower limit is the maximum of 0, where I minus n divided by 2. This tells the math where to start the sum. I minus n divided by 2, because if you are at kernel I equals to 10 and n equals to 5, you want to look at 2 kernels below you. So 10 minus 5 divided by 2 using the integer division gives you kernel 8. So 2.5, yeah, 2, so you're taking the floor. 10 minus 2 kernel 8. Why max? If you're at kernel I equals to 1, you can't look at kernel 1 minus 1 because it doesn't exist. So the maximum of 0 forces the window to stop at the first page 0. Okay, and at 10, and if it's 5, then you don't want to go there. And then the upper limit is basically telling you to do that. Okay, why I plus n divided by 2? Because if you are at kernel I equals to 10 and n equals to 5, you want to look to, okay, minimum, because if you have 96 kernels, the last index is 95. If you are at I equals to 95, you can't look at kernel 97. The minimum is -1, so first do this. Okay. Okay. So this calculation of minimum n minus 1 I plus n divided by 2, this is, and the maximum, this is like a lower limit and a maximum limit for a sliding window. So imagine that you have like these different values, so 0, 1, 2, 3, and 4, and you have like a sliding window. And when you're like starting from the the beginning, right, you can't do this. This is not allowed. So that's why when you're over here, you're basically um you're basically using this maximum part, which is helping you to avoid that particular condition. um and when you are at over here, right, this minimum condition is basically helping you to prevent that. Now comes the part of this I plus n divided by 2 and I minus n divided by 2. So let's take an example, which is that for some reason, let's assume that this is the kernel I equals to 10. Let's assume that this is I equals to 10 and that you have n equals to 5, and when you do you basically want to look in front of you, right? So what you do is you do 10 plus 5 divided by 2, and you take the floor of this, and this will basically give you 2.5, so that means you can take it as 2. So till kernel 12 you can see this. So this is your window over here. And then similarly you do the same for the down values. So this becomes again 2, and then you minus 2, so this becomes I equals to 8, and then you can look at these values. So that's why you're doing your I plus n divided by 2 and your I minus n divided by 2, because it acts like a sliding window where n is basically like telling you the width of this entire um, normalization window. That's pretty cool. So we understand now that what's the importance of this formula and what's the importance of this formula, how was this calculated. Let's take a look at what is these extra parameters, and basically we're basically doing a summation of squares over here. So we look at all of the kernel neighboring values, we sum them up. So if the neighboring values over here so if for example, where's if for example, um, we have a2 as 2, a3 as 10, and we have a4 as 2, then the summation of squares ignoring all of the other parameters would be 2 square plus 10 square plus 2 square, which would give you 4 plus 100 plus 4 equals to 108. But in the other scenario, where if you have a2 as 50, or let me just do it directly, that 50 square plus, now this one is 10 square, and this one is 50 square, then that would basically give you 2500 plus 100 plus 2500, and that would give you 5100. So when we are taking a look at this value over here and this value over here, because remember that you take this thing, so the center value, and then the summation of the entire width goes over here on the right side of the formula. So that basically means 10 divided by 108, and then compare that to 10 divided by 5100. So the smaller the summation will be, the higher ij value will be, which basically means that it has found an edge. So you want this to be smaller. And the higher this value is going to be, sorry, I said it in the opposite way. Sorry. The higher the denominator is, the more bigger this bij value will be. So that basically means that you have found you no 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 um result of the first scenario. So the result of this first one will be dividing by a small number keeps B3 high. The model says this is a very clear unique detection of the feature 3. Yes. So if this is small, the overall numerator becomes bigger, and you say, yes, I see there is an edge. And if the numerator becomes too big, the value in the numerator becomes so small, and you say, no, this is not that good. There's so much noise and activity at the spot that kernel 3 signals isn't reliable or distinct. Okay. Now, this mimics how the human eye works. If you walk into a bright room, your neurons inhibit each other so that you can still see the edges and shapes rather than just a white blur. If an image is suddenly very bright or has a very high contrast, all kernels might output a higher value raw values of AIX, Y. The LRN dampens these uniformly loud spots so that the neighbor only pays attention to the relative strength of a feature compared to its neighbors. Okay, so almost I got the idea. Almost. And I will summarize this in a very nice way at the very end so that you guys can understand what I'm saying. I mean, I'm trying to understand over here, but yeah. Now I just want to understand one more thing before I neatly summarize this entire formula. What is K? What is alpha? And what is beta? And why do they need it? What's the significance of all of these hyperparameters? So what is K, what is alpha, and what is beta? So, um, K, alpha, beta are the hyperparameters tuned on the validation set. If a neuron neighbors have very high activations, its own output is dampened or scaled down. This creates a brightness normalization effect that helps the model to generalize better to this. It divides the original sum. It divides the original activation AIXY by this sum plus constants K alpha. This. Do they explain the constants? Let's see. The ordering of the kernel maps is of course arbitrary and determined before training begins. This sort of response normalization implements a form of lateral inhibition inspired by the type found in real neurons, creating competition for big activities amongst neuron outputs computed using different kernels. The constants k, n, alpha, and beta are hyperparameters whose values are determined using a validation set we used. K equals to 2, n equals to 5, and alpha equals to 10 minus 4, and beta equals to 0.75. We apply this normalization after applying the ReLU nonlinearity in certain layers. Okay, but why? Why did they apply K, alpha, and beta hyperparameters? That's one question. Okay, the safety. The role of K constant is added to the sum before the division happens, so you can prevent the division by 0. Okay. It also acts as a threshold by setting k equals to 2. The authors ensure that if the neighboring activity is very low, the denominator stays small and the neuron's output A isn't reduced too much. Okay, the sensitivity scalar. Alpha is a coefficient that multiplies the sum of the squared activations. Alpha, wait. Okay, so sorry, I wasn't attending to the chats. Ah, yeah, Lamau. Lamau, I totally zoned out. um, yeah, uh, yeah, Lamau. uh, I seriously need to get a good plugin. I seriously need to get a good plugin. Um, yeah, so for people who are joining in right now, I'm sorry. I'm really, really sorry. I wasn't looking at the chat. I didn't even know that there were people who were looking at this. Basically, I'm trying to implement our Alexnet. So there are different sorts of very famous deep learning architectures, um, and I am trying to recreate them because it's very important in research. So I'm starting with the very, very basic architecture that's called Alexnet, and then I'm going to move my way to transformers and more interesting models. So right now I'm doing the most boring thing, which is I'm trying to understand what's the um what's the maths behind this equation? Why is it important? What is its overall effect on the entire architecture? And once I understand what it does, then I'm going to try to use this in my Alexnet paper, maybe. Okay, I'm gonna take a small break um right now. Should have. Can you elaborate your plan to learn AI, please? Okay. So it depends. Um, like my plan is different as compared to what your plan would be. So, it would be better if you could like tell me what you want to learn in AI. But for me, uh, I look at AI in two different aspects. I look at AI with respect to application, which is related to software engineering, how when you have these really good AI models, so for example, you have your ChatGPT or you have your LLM wrappers, how are you using them or incorporating them into business solutions and then using them in your companies and that perspective. So that's application based AIs. And then you see your job roles as machine learning engineers. And this differs. No, I don't have any plan. I'm learning Java, but wanted to know how learning AI works. Um, no, I don't have any plan. I'm learning Java. Okay, that's good that you're learning Java, but wanted to learn how learning AI works. Okay, so I would say if you are just starting out in AI, then a very fun way of how doing or learning or getting into AI without getting very scared is you start using pre-built libraries and you start integrating them in your whatever application that you're trying to build. So um, you don't necessarily need to know Python. There's also, I was like recently reading about this thing called Java ML, and what that is it's like a Java machine learning library. And what you can basically do is you can just use these models directly in your program without knowing how it works. And for you right now, that's more interesting because you don't have to go in the entire mathematics part of it. You don't actually need to know what's happening over there, but at the same time, you're using AI in your workflow, or not in your workflow, but for building applications. So that's a very nice way of like getting into it and like also building up your portfolio. And it's also pretty fun. I mean, you're like using or you're demonstrating to other people that, hey, I can use AI, which is pretty fun. And once you do that, then if you find AI interesting and you want to know how these AI models are basically built, or when you give some data, you're getting some output and you want to understand how this data was being um, generated, then you start your AI plan, which is you start with the very, very simple AI stuff. So let me just show you that AI, deep learning, machine learning. So if I have this image, so you start with AI, and AI can be very, very something very, very simple. It can just be like, hey, like if else conditions. It is still AI. It is still AI. It's just very dumb AI. And then you start learning about how do you add probabilities, how you add different sorts of other information, and then you are like improving your AI models. So then you learn about machine learning, and then you learn about different sorts of like algorithms in machine learning. So, like classification, regression, whatsoever. And then if you want to learn how ChatGPT was built or how an LLM was built, then you learn what is a neural network. I hope I didn't confuse you that much, if that helped you in answering your question. But if you want a roadmap, I can also tell you, like, hey, go to this courses, and you can learn AI like that as well. I can also tell you that. Yeah. Um, yeah, it is very interesting. I mean, if you're very interested, there's let me change my screen a little, just a second. Okay. Yeah. So there is this thing called deeplearning.ai. This guy, Andrew Ng, he is a very, 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 very famous guy in the machine learning world. Um, mhm. Over here, he has a lot of different courses, but the most interesting course for just starting out would be, oh man, this one, build your first app with AI. It's beginner friendly. This one is pretty good. Um, if we go for courses with beginner, this one, machine learning specialization. This will set you up on, if you actually want to like learn what goes into AI, all of the machine learning stuff. This is your go-to place. Okay. Um, yeah, yeah. Let me know if you have more questions. No problem. No problem. Yeah. Back to studying. Okay. So, where was I? Pa, 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 pa. There we go. Do, 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 do. Man, okay. Hello, Annie Rudvarier. How are you doing? Hope you're having a nice day. Fine. How about you? Yeah, I'm also doing pretty good. Um, just started um reading a research paper and looking at crazy or complicated mathematical expressions. So yeah, going pretty good, I would say. Hmm. Yeah. So I was like reading this research paper. This came out back in like 2012. So everything related to any AI which involves images and it involves videos, um, Oh, so this is your first time talking to a YouTuber. Well, I mean, this is my first time talking to my viewers, so that's pretty fun. So yeah, it's pretty fun. So I was just reading this research paper about the very first AI model which was used to detect um, different sorts of like objects in an image or a video. So this would involve, hey, if you give me an image of a tiger or of a leopard, then this is a leopard. If you give me an image of a dog, then it is a dog. I will also stream learning Java. That's pretty good. Nice. You should do it. You should do it. It's pretty fun. Yeah. All right. Let's get back. Okay. So, um, oh, you're doing it. It's pretty good. Okay. So I know what this does. I know what this basically is. Um, Now what was beta again? Beta is the intensity power, the exponent applied to the entire denominator. It controls the contrast of the normalization. Uh, mm, 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 mm. Prevents division by 0. Okay. Okay. So what that basically means is if I have a number over here and let's assume that this is 10 and I divide this by some other number, which is this entire thing. Let's say that this is a constant c. So you're adding this k so that if this c turns to 0, you don't have a mathematical error. So this is like a safety. You're also adding this k because um, you want it to act as a threshold so that if the neighboring activity is very low, the denominator still stays small. Okay, so this is like your your threshold. You're applying alpha because that's basically like saying how much effect you want. Alpha, even tiny amounts of noise. Okay. Hmm. All right. It is time to make some notes. Notes. Uh, okay. Hmm. So, ReLUs have a desirable property that they do not require input. Yeah. So the first thing is AI x comma y. Assume that you have uh, an image of size 5 by 5. The pixel is denoted by x comma y. Assume that you have multiple kernels, so one for vertical edge, horizontal edge, etc., etc. So one you have for a vertical edge and the other one you have for the horizontal edge. Then I basically denotes which kernel you're talking about. So that's AIX comma Y. K is to prevent division by 0, and also a threshold. And the threshold over here would be sure that if the neighboring activity is very low, threshold that if the denominator is too small or the neighboring values are too small, then you're adding a little bit of nudge, or a little bit of nudge, or yeah, just a little bit of nudge to keep some output of the denominator. Okay, what is alpha doing? Alpha is the sensitivity over here. So it's a coefficient that multiplies the sum of the squared activations. It controls how much, okay, sensitivity. How much do the neighbors matter, or how much impact do they have? So it's like a multiplier. So if alpha is very small, perfect. Then we have beta, which is your intensity. So this is basically controlling. This is basically controlling. What is it controlling? It's controlling the contrast of the normalization. Yeah. Okay. Okay. Ah. Okay. Let's get back. Let us get back to the studying. Study, 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 study. Studying. Uh, so that's controlling the contrast of the normalization. Um, so p equals to 1 is linear, which means 2 times the noise equals to half the output. So 0.75 basically means over here 0.75, 0.75 basically means um, making a braking effect slightly smoother. It ensures that as the neighbors get noisier, the suppression increases but not aggressively kills off the information. Okay. Okay, so that's a very important point there. Then we understand what are the hyperparameters now. So All right. Let us begin back where we left off. Um, so what is the central idea of this? The central idea of this entire local response normalization is that if you have your neighboring neurons and they're basically giving some output, right? You want to decrease their noise and you want to basically get an edge to differentiate between what is an object and what is not an object. Because if you didn't had an LRN, if you would get a very bright image, all of the kernels would give you very high values. But if you have the LRN, then you will have some patches which will give you some less values, and that contrast helps you to differentiate. So high total energy, high contrast, the sum is large, the denominator grows, and the volume is turned down for everyone. Total low energy or low. Hmm. The blur problem. In human eye, if you didn't have lateral inhibition, light hitting one part of your retina would bleed into the signals of the neighboring cells, making everything look like a blurry mess. Alexnet's solution says it creates competition by dividing by the activity of the neighbors. A neuron is only allowed to have a high output, BIXY, if it is significantly stronger than the kernels around it. This sharpens the features and helps the model generalize to different lighting conditions. Okay, so so. Mm. Ha da 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 da. Do 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 do. Okay. Yeah. Hello, Alvin. Alvin Vinu. There we go. I think hopefully I took the right name. Alvin Vinu. How are you doing? Uh, yeah. Um, yeah, I'm just reading a research paper. This is an AI research paper. I'm reading the boring mathematics, and then I'm going to try to implement this. Um, yeah, I'm doing pretty good too. Yeah. So just reading this right now, trying to understand what they were saying over here, and then try to implement it. Think I'm uh almost done with the reading part, and then I'll start with the interesting coding part. But yeah, that's basically the plan. Yeah, it is pretty interesting. So, um, I was just reading this mathematics part, and apparently, they take inspiration from real biology. I hope I can find it over here. Yeah, here it is. So they say that they're implementing lateral inhibition, and what that basically means is um, when you're looking at objects in real life, um, the way how your retina works is it turns on one neuron and it then deactivates all of or it suppresses the neighboring neurons. And what that basically does is it allows you to like differentiate different objects in different lighting conditions or in different contrasts. So if you didn't had this thing called lateral inhibition, then what would happen is if you look at any image, may it be in very high lighting or in very low lighting, everything would look very blurry. So that's what our actual eyes are doing in real life. We're basically like whenever we look at something, we turn off some of the neurons and only one neuron is active and we only look at the edges mostly. Subconsciously, we're just looking at the edges and it helps to like differentiate. And it is also pretty um oh thanks for subscribing. And yeah, I mean you don't necessarily need to know anything about software engineering. Um, I mean, you could always like come here and just have a nice conversation. I'm also open to that, not just particularly into like software engineering and maths and all of AI stuff. So we can always have a chill talk about that or conversation about that as well. So yeah, that's basically something very fascinating, which is they try to like replicate that behavior over here. So I was just reading about that. Okay, yeah, I just have to put one more note over here and then I can move on to the next paragraph. Uh, how was your day, by the way? Done with that formula. Now comes this part. Overlapping pooling. Pooling. Oh, tiring with the school and classes. Yeah, I can understand. Are you in school, college, university? Uh, hmm. Okay, overlapping pooling. Traditionally, overlapping pooling summarizes the outputs of the neuron. Pooling window Z by Z is larger than a stride S, specifically names stride 2. School 11, having my finals next week. Well, best of luck, and I can totally understand why it's tiring. I can also understand it could be very annoying as well, especially when you're having your finals and you're like, ah, man, I just want to get done with this. And you're like, oh man, I just wish my finals could be much more closer, or to never, or to like never be close. Um, yeah, I've been there multiple times, multiple times. But yeah, best of luck. Hope it goes well. And we all know that um when you're having your finals, you're always procrastinating to the final moment and then studying. Hello, Sami. How are you doing? Hope you're having a good day. Okay. Okay, now to go into the Oh yeah, I have to add more notes. I forgot to add the sliding window part. N is the total number of kernels. Ah, you're studying maths. I am from BD. I want to know about AI and ML engineering. I am a computer software engineering student. Good. What do you want to know about it? Do you want to understand how to get into AI and ML engineering? Is that your question? Studying maths. Um what are you exactly studying in maths? Like, do you know any topics that you're studying in mathematics? N is the total number of this, and over here is the neighboring neurons. Or yes, but I'm a newbie. Perfect. Okay, so this someone else also asked me the same question, which is, hey, how do I get into AI and ML engineering? Do you have any programming experience? Because I want to understand first, like, at what level you are at, and then I can like maybe help you a bit more. N equals to the neighboring neurons, or the neurons which will be suppressed. Okay, so you're just learning. Perfect. Um, so if you really want to just get into AI and ML engineering, there is this course I mean, it's not my course. It's a course that is really beginner friendly. Um, this is by this guy. His name is Andrew Ng. He is basically from Stanford. He's a very, very famous guy in the AI world. If you've heard of the name Coursera, like there's this place called Coursera where you can do your courses. This guy basically was the founder of Coursera. Now he has launched a new company called deeplearning.ai where he's basically teaching or he's doing loads of different courses on AI. So if you want to learn your first AI course, you can do this one, which is build your first app with AI. And if you want to do or get a bit more into machine learning and AI and understanding how it works, then I would basically suggest you this one. Um, where is it? 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 This one, machine learning specialization. This is something where you can like get into the basics um, of actually how machine learning is done. So if you're scared of AI and you don't like maths too much, then what you could also do is you could look into different AI libraries and try to make an application around that. So for example, you can maybe like import like a library for ChatGPT, and you can think an idea around ChatGPT by saying, hey, maybe I can make a like a planner where I just give all of my daily routines, my examination task, and it gives me a really nice summary of it. That could be a really nice project that you could work on. Or if you are more into images and computer vision, then you could say, okay, maybe when I go to a supermarket, and I don't want to like write down um, all of the items down or all of the groceries down, then you can just take a picture of your bill, and then it could just extract all of the details. So that's also pretty fun to do. Okay, so you're learning limits, derivatives, relations, functions, trigonometry, basic core concepts of maths. Yes. Yeah, I mean, I was like over here, this part, this minimum part and this maximum part is kind of like a limit. So I was also doing the same thing. No, I do not stream every day at this time. Um, because I'm also doing my master's in AI right now. I also have a job. So it's just that whenever I get my free time, I start a stream on the AI stuff. And when I get free time, then I'm basically playing some games and creating a new stream, not on this channel, but on a different channel. Um, so yeah. But sadly, I don't have a routine for now. Too many responsibilities on my head. So that's why. Yeah. Um, yeah, I would say do study. Where am I from? I'm from Pakistan, but right now I'm in Germany. Okay. Mm-hmm. That's done. Right. Um, to 5, and you have to 3. Just a second. 9, 10, 11, 12. So if I have 5, that's 8, 9, 10, 11, 12. Yeah. You're right now. How's life there? Um, yeah. Um, yeah. I hope you can also um get here as well. Well, Germany's life is pretty different, I would say. Um, Language is a barrier over here, so it is little bit difficult to get with life when you don't know how to speak German. But I'm also learning a little bit of German now or then, and it's a little bit better now because the spring is coming up, so the weather is getting a little bit warm. But a few weeks back, it was in single digits, so it was less than 10 degrees centigrade over here, and I had to wear multiple clothings even when I was in my room because it was very cold. So it's pretty nice that the summer is coming back. So it's getting a little bit warmer now. Okay. 8, 9, 10, 11, 12. Good, 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 good. And where are you guys from? I mean, you don't have to say if you don't want to, but it's fine. Uh, okay. Mm-hmm. To see how overlapping works in this, let's take 1D. Oh, that's nice. That's nice. So, Alvin, you're from India, and Sami, you're from Bangladesh. That's pretty nice. Yeah, I have some friends over here as well who are from India and Bangladesh as well. That's nice. Pooling layers and CNN summarize the outputs of neighboring groups of neurons. Okay, so that basically means um where is my so they have a concept of overlapping pooling. So what they're basically saying over here is if you have an image and the pixels are like this, then you can have something called stride. So if the stride is 1, this will go like this: 1, 1, 1, then 1, 1, 1, 1, 1, and 1. But um, whenever we have a bigger um, whenever we have a bigger window size than the stride, so for example, like I was striding over here by 1 by 1 by 1, but over here, since we had a window size of 3 by 3, which is more than 1, you would see that we are overlapping some of the values. So that means this whole thing, let me see if I can show that. So this whole column, that's number 1. Then I move it here. Then this 2 column, I'll just put a tick mark here. So that's second time this has been visited. Then I move this again. Then again. So you're overlapping it over and over again. So that's what they're saying over here, which is when you have your window size greater than your stride, then you will have overlapping pooling, which means that you are revisiting um, you're revisiting some of the pixels, and that will decrease the overfitting. No problem, man. Take care. Have a nice day. And yeah, best of luck for your exams. By using a 3 by 3 window but only moving 2 pixels at a time, Alexnet ensures that its summary of the image is more continuous and less likely to lose important features that happen to fall. Mm-hmm. Sure. Yeah. Let's talk again, maybe in future. If I'm maybe streaming next week, then I'll get to hear about how did your or how were your exams. I'll keep an update on that. Increasing the pooling, wouldn't increasing the pooling. Bye bye. Oh. Okay. Okay. Ooh. Okay, so um, they're basically describing the overall architecture over here, 1000 by 1000 over here. Kernels of the third convolution are connected to all of the kernel maps in the second layer, the neurons and the fully connected layers. Yeah, this is the entire. This is very important. Then they're explaining the data augmentation part over here. The easiest and the most common method to reduce overfitting on an image data is artificially enlarge the dataset using label preserving transformations. So they're using two distinct forms of data augmentation. Okay, let's put that in red for dataset. Um, so the both of which allow transform images to be produced from the original images with very little computation, so the transform images do not need to be stored on the disk. In our implementation, the transform images are generated in the Python code on the CPU, while the GPU is training on the previous batch of images. Oh, this is interesting. So they're training at the same time, they're also computing the transformations on the previous batch of images. That's pretty smart. In the first form of data augmentation consists of generating image translations and horizontal reflections. We do this by extracting random 2 by 2, 2224 by 2224 patches and their horizontal reflections from the 2. So this is the first transformation that they're doing, which is horizontal reflections. And I think 256 by 256 is 2048. Let me verify this. So 256 by 256. Okay, no. 224 by 224? No. Are they adding it? 224 plus 224 by a factor. It's a factor. Okay. So this number, I think, when you divide this by 2048, you get 32. No, I still don't understand how. So they had to do it because it would overfit regardless. Data augmentation is very important. Always do data augmentation because that can lead to overfitting. Without this scheme, our network suffers from substantial overfitting, which would force us to use much smaller networks. At test time, the network makes a prediction by extracting 52224 by 2224 patches, the four corner patches, and the center patch, as well as their horizontal reflections, and averaging the predictions. The second form of the data augmentation was, yeah, this one. They applied PCA on this. So they applied horizontal reflection and they also applied PCA. I have to revise what PCA was. Yeah, they're applying dropout. This comes in the method. In training time, they were just multiplying it 0.5. But why? Co-adaptations, this is important. Okay, so I'm going to pause the stream. I'm not gonna end it right now. But I'll be right back. So let me add a this. There you go. And we shall do something. Wait, what? Oh, I did not know that my entire screen was not being captured. But anyways, let's put that as this. All right. So I'm going to now end the stream. And yeah, I'm going to implement this architecture in the next stream now. So have a nice day, everybody. Bye bye.